All right, here's Algebra, week 4. We have a lesson with a worksheet. It's labeled quiz, but it's just a worksheet. Another lesson with a book assignment, another lesson with a book assignment, and then a quiz. Again, if you have any questions or you just need to contact me, there's my email. All right, let's get started. So the first lesson, we are on 10.4C, actually the third day on it, is on circular permutations. So we did permutations last week, or 2 weeks ago when we had our last lesson. Permutation is where order matters. Circular permutation would just be a permutation that's in a circle. So a group arranged in a certain order in a circle. Now, if it's just a permutation, if you remember permutation, like 4 people in a line, that was just 4 factorial, which is 24. So the formula for a permutation was n factorial. If it's a circular permutation, the formula is n minus 1 factorial. So for example, let's say we arrange 6 CDs in a tray. All right, so we just get a visual of that. Here are the 6 CDs. Now, since they're in a circle, if we turn this counterclockwise or clockwise, there might be a different one at the top, but it's still in the same order. So in other words, this order is the same as if we move them all clockwise, put F at the top. So these are the same. So that's where the minus 1 comes from. So if it's in a circle, we're going to subtract 1. So this problem isn't 6 factorial, but it's 6 minus 1 factorial, which is 5 factorial. If you remember what factorial means, that just means 5 times 4 times 3 times 2 times 1. We could do it that way, or we could just use the calculator. 5 factorial, I actually got it in the calculator right now. So we go 5, math, we go to probability, and then that's 4. 5 factorial is 120. Now, if we have a circular permutation with a fixed point, sometimes the book calls it a clasp, then the formula goes back to just a normal permutation, which is n factorial. So for example, let's say we have 4 people with the baby in the front of the table. How many ways can they sit? Now, the baby has to sit at the head of the table, so I'll just call that baby. And let's just say there's a mom, whatever, sister, dad. So that would be one possibility. Now, we can rotate those three, but the baby stays in front. So by rotating, putting dad here, mom there, and a sister there, these are different, right? Because now you can see the baby was between dad and mom. Now the baby's between sister and dad. All right, so unlike this one where if we rotate it, that's still the same thing. This is not the same thing, thus we are not subtracting one there. There are more answers here. So this is the same as a regular permutation as if they were just in a line. And we only have 3 people moving, so the n is actually 3. This is a fixed point. Right? This doesn't even have to be a person. Maybe this is a flowers, right? The being around a vase of flowers. All right, so this is just going to be 3 factorial, which is 3 times 2 times 1, which is 6. The last thing from this section deals with reflection. A reflection is an arrangement seen from 2 different views. Without changing the arrangement. All right, what that is kind of like if you can like pick up something and see it from 2 different views. Give you an example, key rings. Let me just take this thing off here. Key rings, necklaces, bracelets. Those are things that are kind of reflections. So for example, if I said which key is to the right, you would say this one. But I could easily flip this around and now you would say this one. All right, so you can't do that with a CD tray or a table or whatever. So like no matter how I move, like I could try to rearrange these any way I like, the small key will be between the 2 big keys. There's no way I can't have that happen. Whereas if it's at a table, there is a difference between being on the right side of it and being on the left side of the table. Where this one, I can be on the right or left just by flipping it around. So a reflection basically is something that you can hold and turn upside down. All right. So in this case, if I have this problem here, 3 keys on a circular ring. Oh, I got to give you the formula. If it's a reflection, we cut the answer in half. All right, so in this case, there's only one way to rearrange these. So like I said, you can put these keys however you want. It's going to be the middle key. The small key is between the other 2 keys. And you could say it's on the right, you could say it's on the left by just flipping it around. So the formula for reflection is, so it's n minus 1 because it's a circular factorial, but then we're going to divide by 2. So in this case, we have 3 keys, so 3 minus 1 factorial divided by 2. Well, 3 minus 1 is 2 factorial. 2 factorial is just 2 times 1, which is 2. 2 divided by 2 is 1. So there is only one way to put 3 keys on a key ring. It will always be this. There's no other way you can do it. But then the last thing is, let's take this same problem. 3 keys on a circular ring. With a clasp or a fixed point. So I'm going to put that clasp, or whatever you want to call this thing, back on here. So I want to know how many ways can I rearrange the keys with this fixed point. A little hard for me to get this back on there. There we go. All right, so as you can see, right now, the two keys that are touching the fixed point are the big keys. On this side it's here, on this side it's here. I mean, I can flip it around, it's still the same thing. The little key is not right next to it. But now, if I do move one of the keys, all right, let's just take this one off. And let's move it in here. Well, now you can see the little key is touching the fixed point, so that is a different arrangement. So again, with the clasp, if you remember from before, with the clasp, we are not subtracting 1. So it's just going to be n factorial. It is still a reflection. I still can flip it upside down, so I will still divide by 2. But in this case, it's 3 factorial divided by 2. And we could do the work on the calculator if we want. 3, math, go to probability, 4, divided by 2, and there's your answer, 3. And that's the first lesson. The homework for that is this worksheet. It says quiz, but this will just be a worksheet. It's an old quiz of mine, but I didn't have that many problems with the circular permutation, so here is the homework for that day. All right, 10.5 is on multiple stage experiments. So far we've just been doing kind of like one experiment for the most part. We've actually done this a little bit, like flipping 2 coins or flipping 3 coins. For the most part, we've just done one experiment. All right, so let's say you are, shooting 2 free throws. Shoot 2 free throws. All right, so on the first attempt, you're either going to make it or miss it. Now, I don't want to write M and M because they both start with the letter M, so we'll just say yes means that you made it, no means that you missed it. And let's say that your chance of making it is 60%. So then your chance of missing would be 40%. So that's the first attempt. Now on the second attempt, again, you can either make it or miss, make it or miss. But on the second one, if you made the first one, let's just say your confidence got a little better. You have an 80% chance of making it, 20% chance of missing it. Where on this over here, if you missed the first one, maybe your confidence is shot a little bit. You only got a 30% chance of making it and a 70% chance of missing. So all of this is done for you. All right, so this is all done. What they'll say is list the outcomes and each probability. The probability for each of the outcomes. All right, so we're going to go across, and like we did with the flipping the coins, we're going to multiply. So the first possibility is make. And we're going to multiply 0.6 times 0.8. Well, if 6 times 8 is 48, 0.6 times 0.8 is 0.48. So you have a 48% chance of making them both. The second scenario would be a make and a miss. 0.6 times 0.2 is 0.12. The third outcome is a miss and then a make. So that is different than the first one. All right, this one you made it and then missed. This one you missed and then made it. That's 0.4 times 0.3, which is 0.12. These don't have to be the same. They tend to be the same in a lot of my examples, but they don't have to be. And then the last example or last outcome would be two misses. 0.4 times 0.7 is 0.28. These four numbers need to add up to 1, which they do. And those are your four outcomes. Okay. And then they might ask questions like, what's the probability of 2 makes? Now, a lot of these answers are going to be right off the diagram, so I can just take it right from there. There's 2 makes. What's the probability of 1 make? I'm going to come back to that one. Let's do this one first. 0 makes would be 2 misses. So here's 0 makes down here. That's 0.28. Now 1 make is both of these. So we need to add both those together. So 0.12 plus 0.12 is 0.24. Here's a new one. Probability of making the second, that's y sub 2, given, this is a vertical line, you made the first. So let me actually just write what that's saying. The probability of y2 given y1. Or if this is a basketball problem, the probability of making the second given you made the first. Now that question's different than 2 makes. This one is saying you already made the first. So this is done. This is 100%. You made this free throw. So what's the probability of making the second free throw if you already made the first one? Well, that answer is just right here. Here's the probability of making the second one given you made the first one. So anytime you have this given problem where you're working left to right, the answer is going to be one of these four. Let's just do another example. The probability of making the second given you missed the first. So again, it's given that we missed the first. So this happened. So what's the probability of making the second given we missed the first one? It's right here. Here's the probability of making the second given you missed the first. And that was 0.3. All right, let's go to the 3 coins are flipped problem. Let's complete tree diagram. With outcomes and probability. All right, so the first coin is flipped. It's either heads or tails. And it's obviously 1/2 for both. You got a half chance of getting a heads, half chance of getting a tails. On the second flip, again, I can get a heads or a tails, and again, they are also 1/2. Down here is the same thing. Anytime I break them up, there's going to be 2 possibilities, heads and tails. Now that's 2 tosses. So here's first toss. Here's the second toss. Now the third toss is going to get a little messy. Third toss is over here. We need to break each of these up. Heads, tails. Heads, tails. Like I said, a little messy here. Heads, tails, each with a half. And heads, tails. The bigger you draw it, the easier it is. Mine's kind of small. I should have made it a little bigger. All right, so now we go through all our outcomes. Heads, heads, heads. Now when I multiply, it seems like in every single scenario, it's 1/2 times 1/2 times 1/2. Well, if we multiply the top, 1 times 1 times 1 is 1. If we multiply the bottom, 2 times 2 is 4, times 2 is 8. So all of these outcomes are going to be 1/8. So the second one is heads, heads, tails. And again, these are all going to be 1/8. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads. Getting a little crunched together here. Hopefully you can see it. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. So there's your tree diagram with the outcomes and the probabilities. Again, these are the outcomes, these are the probabilities. Okay, now we want to draw a tree diagram where we pick 2 marbles from 3 blue, 1 red. There's going to be 2 parts from it. The first part is going to be blue. First part's going to be without replacement. So that means we are not putting it back. All right, so on the first pick, again, one of 2 things are going to happen. You're either going to pick a blue or you're going to pick a red. The chance of getting a blue would be 3 out of the total, which is 4. So there are 4 marbles, 3 of them are blue. The chance of getting a red would be 1/4. Again, each of these branches have to add up to 1, just like the coin problem, just like the free throw problem. Each branch has to add up to 1. Whether you have decimals or fractions, they have to add up to 1. Now here's the tricky part. All right, you are picking 2, so now we need to branch them off again. So it'll look like this one. This is 2 events here. This one was 3, that's why it was a little bigger. So we need to branch these off again. And then this is the second pick. Again, we can get blue or red. But here's where it gets tricky. Let me just put blue and red down here too. We're not replacing it. So you almost have to act out the problem. What I like to do sometimes is just off to the side, just act out the problem. All right, we got 3 blue and we got 1 red. So we have to act through both these scenarios. So the top scenario is we caught a blue first. All right, so I'm going to cover up the blue. Okay, now when I pick again, there's only 3 marbles left. Well, what's the chance of getting a blue again? Well, looks like it's 2 out of 3. And then what would the probability of picking a red be? That would be 1 out of 3. Because we are not replacing it. So on the second pick, there's only 3 marbles. Now what some people do is they think that those are the same answers that go down here, but that's not true. Down here, we picked a red first. We got to act out that. So cover up the red. Okay, if you pick a red first, what's your chance of getting a blue? Well, that's 3 out of 3. You could put 1, but you'll see why I put 3 out of 3 in a little bit. And then what's your chance of getting a second red? Well, that would be 0 out of 3, because you can't get 2 reds if there's only 1 red to begin with. So we're going to write down our 4 outcomes. Blue, blue. Here's blue, red. Here's red, blue. And here's red, red. And then to get the probability of each, we multiply. Now, here's why I didn't reduce these fractions down, because in all of them, the bottom number is 4 times 3. So in each of these, it's going to be 12. 4 times 3, 4 times 3, 4 times 3, 4 times 3. That's why I didn't reduce it. That makes it easier to multiply these. And then when we multiply the top numbers, 3 times 2 is 6, 3 times 1 is 3, 1 times 3 is 3, 1 times 0 is 0. And here's your answers. We can reduce them. You actually don't have to, but you could. This is 1/2, and these are 1/4. But you don't even have to do this, and this is 0. These 4 numbers have to add up to 1, which they do. Now let's do the same problem, but this time it's going to be with replacement. So what that means is after I pick a marble, I'm going to put it back. So you actually can pick the same marble twice. Now the skeleton or the branches will look the same. All right, and the outcomes will actually be the same too, but our numbers are going to change a little. So on the first one, again, I could pick a blue and a red, or a red, I should say. And again, the probability hasn't changed. 3 out of 4 are blue, 1 out of 4 are red. Now on the second pick, again, we branch them off. And again, this is blue and red, and blue and red. But this one, with replacement, actually is, to me, an easier problem. We don't even have to act it out. If I'm putting the marble back, the chance of getting a blue every pick is going to stay the same. Whether I pick 2, 3, I can pick 100 times, I am still always going to have a 3 and 4 chance. So wherever I see a blue, I could just put 3/4. And wherever I see a red, I can put 1/4. I don't even have to act the problem out because I am always putting the marble back. We have 4 possibilities. Again, blue, 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 red, red, blue, and red, red. Again, I kind of like to look at the denominator. The denominator is 4 in all these, so 4 times 4 is 16. And now I just have to multiply the top numbers. 3 times 3 is 9, 3 times 1 is 3, 1 times 3 is 3, and 1 times 1 is 1. And these have to add up to 1, which they do. That's 16 out of 16. Now you might say, well, wait a minute. How could you get 2 reds? How is that possible? Well, remember, you are putting it back. So you could pick a red, put it back in, and pick it again. So it is possible to pick 2 reds if you're putting it back. The final thing from this section is, and we've talked about this a little bit already, if we have independent events and dependent events. I should maybe do the dependent one first. One event does depend on the other. So one choice does affect the other. An example of that could be the amount of money you have and what you buy. If you only have $10, that limits your choices of what you want to buy at the store. Whereas if you have $1,000, well, you have more choices then. Where independent is one choice doesn't affect the other. So those are just two random things. Maybe what you ate for breakfast and what you're wearing. All right, it doesn't matter. Those two things really don't affect each other. All right, what I ate for breakfast and what I'm wearing have nothing to do with each other. So now we can go back to the previous problem and say which one of these was independent and which one was dependent. So which one caused a change in the other one? Which one depended on the first pick? Well, that would be the one without replacement. The second choice was affected by the first choice, especially like if you look down here, if I chose a red, that affected getting a red the second time, all right, or whatever, blue or anything. So the first choice affects the second one. So this is an example of a dependent event where one choice does affect the other. Over here, since we are replacing it, it didn't matter what I picked the first time. The probabilities will stay the same no matter what. All right, so this would be an independent example, independent event. Going back to the coin flip, again, one coin did not affect the other. No matter how many times you flip the coin, you have a 50% chance of getting the heads or tails. So this also is an example of a independent event. So that's the second lesson. Then the third and final lesson of the week is 10.6. Expected values. What that means is it's the average value found by multiplying outcomes by probability and